that in fact 3I Atlas gets near Jupiter on March 16th, 2026, at a distance which is exactly identical to the distance inside of which
3I Atlas appears to be performing a move that no natural object should be able to do, and it is slowing near Jupiter with a level of accuracy that looks almost intentional. The object is approaching the edge of Jupiter's Hill sphere, which is the thin boundary where the planet's gravity begins to lose control to the Sun, and this position is so exact that it feels like a deliberate stop. No known comet has ever shown this kind of precise behavior, and the scene has raised new questions about what is guiding its motion. If this is not a natural path, then what is shaping its next step? The journey of 3I Atlas through the solar system has become one of the most unusual stories in modern astronomy, and its approach toward Jupiter began long before anyone noticed a strange change in its motion. The object first appeared as a distant speck moving in from deep interstellar space, and at that time it followed a normal hyperbolic path that matched what scientists expected from a visitor not born in our system. Its speed, direction, and shape all looked natural, so researchers believed they were observing another rare traveler that would pass through and leave without any major surprises. However, its behavior began to shift after it moved closer to the Sun, and this slow change is now at the center of the debate about whether the object is reacting to something or adjusting itself. The topic becomes more interesting when we look at how 3I Atlas responded to sunlight, because the object showed a non-gravitational acceleration right after it passed perihelion, which is the point of closest approach to the Sun. This acceleration pushed it slightly away from its original track, and while the force was weak, the direction of that push was almost perfect for guiding the object toward the position it is now heading for. Scientists have seen comets change their speed due to jets of gas released by heating, yet these jets usually act in random or chaotic ways. Most comets twist, spin, and wobble as they warm up, and their tiny thrusts lead to uneven motion that rarely forms a clean pattern. Atlas behaved differently, and this difference is what led many astronomers to believe that the object is not simply drifting, but is being guided by internal forces or structural properties that we do not fully understand. Another important part of the journey is that the deviation was detected by more than 200 observatories around the world, and each new set of observations refined the same conclusion. The object was no longer following the path predicted by gravity alone, and every updated model showed a growing match between its new route and the boundary of Jupiter's Hill sphere. This level of agreement across global datasets makes the change in direction difficult to dismiss, especially because the acceleration pushed Atlas by exactly the amount needed to reach its current target. The effect could still be natural, but the combination of timing, angle, and precision has kept the scientific community deeply involved in trying to understand what exactly is happening. What makes the story even more surprising is that Atlas did not display any major signs of instability or fragmentation as it moved inward, which is something many interstellar objects tend to show when they experience strong heating. Instead of falling apart, it grew more stable and continued to drift with calm and steady motion. This smooth behavior supported the idea that the object might have an unusual structure or chemistry that helps it stay intact under intense radiation. When we connect all these details, it becomes clear that the current maneuver near Jupiter is not an isolated moment, but the result of a long chain of small and precise moves that started months earlier near the Sun. The pattern raises a serious question about what kind of forces can maintain such a consistent and well-aligned journey. If this motion came from random outgassing, then why did it create such a clean direction toward a single point in space? And if it was not random, then what mechanism could shape the path of an interstellar object so accurately? These questions lead us toward the next part of the story, because the answer may lie in the extreme precision that defines its current approach. The extreme precision in 3I Atlas's current path is the most surprising part of the entire event, and the numbers behind this alignment reveal how unusual the situation truly is. The object is expected to pass by Jupiter at a distance of about 33.24 million miles, yet recent measurements show that it is arriving only about 35,000 miles away from the exact boundary where Jupiter's pull balances the Sun's. This means the error is 1 part in 26,000, which is a level of accuracy rarely seen even in controlled space missions. To understand how strange this is, imagine throwing a needle from Los Angeles and having it land perfectly on the edge of a coin placed in New York. This kind of precision does not appear in natural motion often, especially when the traveler has crossed billions of miles of open space. The significance becomes even more clear when we look at how interstellar objects normally behave, because they usually enter the solar system with unpredictable rotations and uneven surfaces that react differently to sunlight. Small changes in heating can push them in many directions, so their final path is difficult to predict. Even with advanced models, astronomers usually expect a wide range of possible outcomes. Atlas has broken that expectation, and every new update shows a slimmer margin of error instead of a wider one. This growing accuracy is not simply a scientific curiosity because it suggests that the object is following a clean and stable line that does not match the noisy patterns of natural comet motion. The numbers also show that this precise approach did not happen slowly over many months, but began very sharply after the object passed close to the Sun. The slight acceleration that shifted its path created exactly the correction needed for it to slide into the narrow zone around Jupiter's Hill sphere. If the acceleration had been stronger or weaker by even a small amount, the object would miss the boundary by millions of miles. The chance of a natural push happening at the exact strength and direction required is extremely low, and this is why many researchers are questioning whether this motion can be described with simple physics alone. The effect resembles a final steering adjustment used in spacecraft navigation rather than a random burst of gas. The alignment also matters because the Hill sphere is not a target that natural objects normally approach so closely. When comets enter the region near Jupiter, they are usually dragged inward or pushed away, and they rarely stop near the outer edge. The fact that Atlas is not falling into Jupiter's deeper gravity, but instead sliding next to the boundary, makes the movement appear even more deliberate. In many ways, this looks like a controlled approach that ends at a point where gravitational forces nearly cancel out, which is a situation more familiar to planned missions than wandering debris. When we combine the tiny error, the sharp correction near the Sun, and the unusual target, it becomes clear that this is not a normal trajectory. Something is keeping the object aligned on a path that matches a single mathematical line across millions of miles of space. If this is a coincidence, it would be one of the rarest ever recorded in astronomy. If it is not a coincidence, then the next question becomes even more important. What kind of process can guide an interstellar object with such perfect timing and accuracy? The Hill sphere of Jupiter is one of the most important gravitational structures in our solar system, and understanding why it matters helps explain why Atlas's behavior is so unusual. The Hill sphere marks the region where a planet's gravity becomes stronger than the pull of the Sun, and for Jupiter, this region stretches across tens of millions of miles. Most natural objects never hit this boundary because their paths are shaped by chaotic forces like solar radiation, collisions, or uneven outgassing. They either fall deeper into Jupiter's pull or stay far outside its influence, and this pattern makes the boundary more like a mathematical line than a physical target. Since no object normally aims for this thin transition zone, the fact that Atlas is approaching it so precisely is already surprising. This boundary is also unique because the forces inside it behave differently from the forces outside. When an object enters the Hill sphere, Jupiter's gravity begins to dominate, and the object can be captured or accelerated. When an object remains outside, the Sun's gravity takes the lead, and the motion becomes more stable and predictable. The edge between these two regions is a fragile border where a small shift in direction or speed can create two completely different futures. Because of this, it is extremely rare for any comet to match the exact distance where the gravitational powers balance each other. The boundary is not a place where natural bodies stop, slow down, or adjust their direction in a controlled way. The comparison becomes even clearer when we look at how space agencies use gravity. When engineers design spacecraft routes, they rely on the deep gravitational wells of planets like Jupiter to perform slingshot maneuvers. These maneuvers require careful planning and precise timing because even a slight misalignment can push a spacecraft into a totally different orbit. For example, missing the edge of the Hill sphere by only a few thousand miles can shift a mission by millions of miles later in the journey. It is challenging even for human technology to reach this boundary with exact accuracy, so seeing an interstellar object behave with similar precision raises important questions about the forces acting on it. Another detail that stands out is the narrowness of this transition region. While the entire Hill sphere is huge, the exact boundary where the control changes from Jupiter to the Sun is extremely thin when compared to the surrounding space. Hitting this specific line is like landing on the edge of a moving shadow, because the position changes slightly with each orbit. This makes Atlas's alignment even harder to explain through random chance. The more we study it, the clearer it becomes that the approach is too clean and too steady to be typical for a natural body that has traveled for millions of years through unknown environments. All of this leads to a difficult question. If the Hill sphere is not a place where objects naturally aim or stop, then why is Atlas positioning itself so perfectly along this invisible line? The idea of a precision parking maneuver becomes easier to understand once we look at the way 3I Atlas changed its direction after passing the Sun, because this small shift appears to match what a controlled adjustment would look like during a space mission. The object received a gentle push that moved it away from its earlier path, and the amount of that push was almost exactly what was required to guide it toward the edge of Jupiter's Hill sphere. Natural comets do experience small forces from gas jets when their surfaces heat up, yet those jets act in irregular ways that normally send objects into messy or unpredictable motion. Atlas has not shown that kind of chaotic behavior, and instead it has continued along a steady line that keeps matching new predictions with surprising accuracy. One reason the shift feels deliberate is that the correction happened at the perfect time, since a change made far earlier or later in the journey would not bring Atlas to the narrow boundary it is approaching now. The timing is important because the solar system is full of moving bodies, varying sunlight, and other forces that can push an object off course. Most cometary jets fire in bursts, and these bursts tend to cancel each other out rather than form a clean direction. If Atlas acted like a normal comet, its path would drift millions of miles away from the region it is now approaching. Instead, the push it received made a clean adjustment that placed it on a path that lines up with a single mathematical point in space. The motion becomes even more interesting when we compare it with standard navigation methods used in human space travel. A spacecraft planning to reach a small or delicate point in space often performs a late course correction after passing a massive object like the Sun, and this correction is designed to fine-tune its route with minimal energy. Atlas fits this pattern because it adjusted itself after passing perihelion and then followed the corrected line with almost no drift. The way it holds this route gives the impression of a system that is reacting to gravitational forces in a controlled manner, and this is why some researchers describe it as behaving like a probe instead of a simple natural rock. The choice of destination also adds weight to the idea of a maneuver, because the outer edge of Jupiter's Hill sphere is a point where small forces can create large effects. It is a zone where the gravitational pull of Jupiter and the Sun compete with each other, and that makes it a sensitive place where objects can slow down or change their behavior. A natural comet would usually be pulled inward or pushed outward long before reaching this zone, yet Atlas is gliding along the boundary with surprising stability. This stability supports the idea that the object may possess certain physical properties that allow it to stay balanced in ways most comets cannot. When we put these pieces together, the picture becomes more mysterious because the shift near the Sun, the stable route, and the unusual target all match what we would expect from a carefully executed adjustment. If this was an accidental outcome, the odds of everything aligning so perfectly would be extremely low. If it was not accidental, then we must consider a more serious question. What kind of internal process could produce a maneuver that looks so much like a planned action? The question of what is guiding 3I Atlas becomes even more complex when we look at the four main explanations scientists have proposed, because each one tries to describe a situation that has almost no precedent in known astronomy. The most conservative idea is that the trajectory we see today might be the result of observational errors, since early measurements of fast-moving objects can contain small mistakes. However, more than 230 observatories have now tracked Atlas, and every new dataset has continued to confirm the same path with shrinking margins of uncertainty. This level of agreement makes the error explanation harder to support, especially because the object keeps matching predictions with unusual precision. A second possibility is that Atlas is being pushed by outgassing in a rare but natural way, since heating can trigger repeated jets of gas that move a comet gently in one direction. This can happen if the jets line up with cracks or weak spots on the surface, and under the right circumstances, they can create a force that looks more organized than random. The problem with this explanation is that the jets would need to fire at exactly the right strength and angle for a long period of time, and even a small change would send Atlas far away from its current target. The chain of coincidences required makes this scenario possible but very unlikely. A third explanation is simple coincidence, because the solar system has existed for billions of years, and it is likely that many interstellar objects have visited without being detected. If even a few of them pass near Jupiter's Hill sphere by chance, Atlas could be another example of a rare but natural event. This is not impossible, but the rarity of the alignment and the clean path leading to this moment make coincidence a weaker answer than many would prefer. The fourth idea is the most debated, since it suggests that Atlas might be reacting to forces in a controlled or semi-controlled way. This does not require the object to be artificial, because a unique structure or chemical makeup could allow it to use sunlight, gravity, or internal processes to guide itself without technology. Some researchers have also proposed that an advanced civilization, if one exists, might navigate through planetary systems by using gravity wells and boundary zones like Jupiter's Hill sphere. While there is no direct evidence for this theory, the behavior of Atlas has kept the question open. These four explanations form a map of possibilities, yet none of them close the mystery completely. If the answer is not error, coincidence, or normal outgassing, then what kind of process could produce such a steady and precise journey? Jupiter has always played a special role in the solar system, and understanding why 3I Atlas is heading toward this planet helps explain why some scientists think its current path may involve something more than simple physics. Jupiter is the largest planet we have, and its gravity is so powerful that space agencies often use it as a natural engine to redirect spacecraft with very little fuel. A single pass near the planet can speed up a mission, slow it down, or send it toward a completely different direction. This is why Jupiter is sometimes called a navigation gate, because its gravity well can shape the movement of anything that enters its reach. The outer edge of Jupiter's Hill sphere is even more important because it marks the place where the pull of Jupiter balances the pull of the Sun. This balance creates sensitive regions where a tiny change in speed can produce a large adjustment in direction. These spots act like stepping stones that spacecraft can use to remain in a stable position with minimal effort. Engineers have spent decades calculating how to reach these zones, and even with modern technology, it requires careful timing and extremely accurate maneuvering. When we compare this with Atlas's clean and steady approach, the similarity is difficult to ignore. Another reason Jupiter matters is that gravity wells like this one can help any object, natural or artificial, move through a planetary system without using much energy. If an object wanted to save power, gather information, or perform some kind of transfer between trajectories, this boundary would be a logical place to pass through. Even natural bodies can experience dramatic effects when entering such a zone, yet Atlas is moving into it with a level of calm that suggests more control than chance. This unusual steadiness raises questions about whether the object may be using this gravitational landscape in a way that we do not fully understand. The fact that Atlas appears to be slowing near this region makes the moment even more mysterious because a slowdown near the Hill sphere could mean the object is preparing for another shift. It could change direction, pause briefly, or interact with the gravitational field in a way that produces new motion. These possibilities make Jupiter an important key in the mystery, since the planet provides the exact environment where small forces can make a big difference. If Jupiter truly acts as a gateway for motion inside the solar system, then what will Atlas do once it reaches the edge of this massive gravitational frontier? The approach of 3I Atlas toward Jupiter has created three major scientific scenarios that experts believe could unfold in the coming weeks, and each one has the potential to change how we understand interstellar objects. The first possibility is that the object may break apart as it reaches the edge of the Hill sphere, since the competing pull between Jupiter and the Sun can create strong tidal stress. Many comets crack when exposed to rapid changes in gravity, and fragmentation could reveal the internal structure of Atlas in a way that no telescope has ever seen. If it has layers, cavities, or unusual materials inside, the breakup could expose them and provide direct evidence of how it formed in another star system. This scenario would give scientists a rare chance to study debris from outside the solar system, yet it would also raise new questions about how the object survived its journey until now. The second scenario is more mysterious because some researchers believe Atlas could release smaller bodies or particles as it slows near the boundary. Natural objects sometimes shed fragments, but doing so near a gravitational transition zone could suggest a more organized process. If Atlas drops small pieces that follow stable orbits or drift in recognizable patterns, astronomers would study the shapes and movements of the fragments to see whether they behave like normal comet debris. Any pattern that looks too neat or coordinated would challenge our understanding of what an interstellar object can do. The idea of a payload release sounds dramatic, yet even a small cluster of fragments moving together could lead to serious discussion about the purpose of the object's visit. The third scenario is the most surprising, because Atlas may change direction again once it reaches the outer edge of Jupiter's domain. A shift in motion could show that the object is sensitive to the gravitational landscape and capable of reacting in ways that do not fit the model of a simple comet. If it turns toward a new path, slows down further, or enters a temporary orbit around Jupiter, scientists would gain evidence that its motion involves more than random forces. A sudden change would also give researchers the chance to refine their models and compare the behavior to what is seen in controlled spacecraft maneuvers. Even a slight adjustment could become one of the most important clues in the entire investigation. These three possibilities highlight how unusual this moment is, because each scenario reveals different secrets about Atlas and the forces shaping its journey. If the object breaks apart, releases fragments, or shifts direction, the results will change the questions scientists ask about interstellar motion. And if one of these possibilities becomes real, what will it reveal about the true nature of the traveler approaching Jupiter? The journey of 3I Atlas now feels less like a random passage and more like a series of careful choices, because its perfect stop at Jupiter's boundary suggests a level of purpose that natural objects rarely show. The alignment, the timing, and the calm approach all point toward a moment that could reveal something far greater than a simple comet. What happens next may shape the way we think about visitors from outside the solar system. If this stop was intentional, then what is Atlas preparing to do when it moves again? Share your thoughts below, and remember to like, share, and subscribe for more investigations.